morning, everybody.
Morning.
It's very nice to see a couple of faces. It's already familiar to me, but still, there are majority of the faces which I am not familiar. So I am Guru my name is Guru from University of Mysore. I've been working for the university for the last 18 years, and I am here today, this morning, to engage you all for about 3 hours, boring and hitting, starting, whatnot, everything. To speak on the algorithms for the minimum spanning tree. So Sridevi Madam said she speaks on image processing. Of course, generally I am known for image processing because my area of research, my research expertise is in the field of image processing and pattern recognition. But out of my teaching interest, so I also teach sometimes my master's students and people of researchers, graph algorithms, mathematics, statistics. Out of my interest from my childhood. Basically, though I am currently a computer scientist and basically a mathematician, I would love to categorize myself as more a mathematician rather than a computer scientist. But my profession, my degrees are all computer science, but I like to be more a mathematician. So anyway, hope we have been attending for the last 3 to 4 days the theory of graphs, complexity of algorithms. I think a couple of my good colleagues presented you to, I must have taken you to the corridor of graph theory using various parameters of graphs and algorithms associated with some of the problems in graph theory, like connectedness, searching for a vertex of your interest, finding out route to a destination, finding out the shortest way of reaching the destination from the source, and looking for all possible ways of reaching a destination from the source. Right? So, but here today, in this morning, my interest goes towards a specialized subgraph of a graph G. What interests me? Every graph G has a subgraph, proper subgraphs. And one of the most important aspects, the important component, a quite popular subgraph of a graph G called a spanning tree, right? Then later I will move on to finding out spanning trees in a general graph, and then in a specific graph called weighted graphs. Hope I need not to define what is weighted graph. It's a graph where every edge has been given a weight. Maybe negative or maybe positive, irrespective of it, but every edge is with a cost. Cost may be a function of several other parameters, right? But still, I am with a graph of vertices and edges where every edge is with a weight. That's what it's weight. Then finally, I move on to how to extract spanning trees, particularly in a weighted graph. And then, if there are possibly many spanning trees, then my interest would always go towards the one which has got a total minimum weight. So such a graph, such as a graph, simply what is called minimum spanning. So before I get into the algorithms of the spanning trees and minimum spanning trees in a weighted graph, let me just take you with the background of a tree. And did anybody have found tree so far? So far in the school of graph algorithms. Now what is a tree then? A connected aside. So what are the parameters of graphs generally?
It is normally in a data structure.
Pardon? want you to define what is actually a graph, but my question is on the parameters of graph. Good. Generally, we represent the graph by number of vertices n, and then edges. Edge is the weight. That's a different aspect of graph, but that's not a parameter of the graph, right? The number of vertices present in the graph, number of edges, and graph has been characterized, either as a connected or as a disconnected. Those are different, adjectives also with the graph. So generally we associate graph with the number of vertices and number of edges. Pardon? Height? No. So when you speak about particularly the tree concept, then you speak about the height, the depth of the tree. Okay. So height is not a parameter of the graph. Then perhaps today I will introduce to you what is called or the rank mu the nullity. Right? In case of a planarity, we speak about number of cases. Right? In case of a planarity, we speak about number of cases, and more than in case of a disconnected graph, we speak about the number of compounds. So generally, these are the parameters which describe any graph G in general. As I said, given a graph G, I can always look for a subgraph. I can always look for a subgraph. I mean, the one which is well inside the graph. I am not looking at the entire, the whole graph. Perhaps my concentration would go towards only some of the edges, some of the vertices of the graph G. And such a pod is generally called a subgraph of G. But here my concentration is not any subgraph of G, but a very specific subgraph of G, which is I go for selectively choosing only those edges. Selectively choosing only few edges from the graph G such that its selected edges are all put together, preserving their adjacency relationship, right? Preserving their incidence relationship. Along with associated vertices I am talking about them, right? Then when I selectively choose only those edges and observe only them, and I see that pod does not contain any circuit, any cyclic, and generally it is called a tree subgraph. Okay? So here my concentration is on acyclic, means a tree subgraph. A tree subgraph. So what is a tree? As you said, it is not only acyclic, it is also connected. So basically we have the following property of a graph. Number one, the connected, and it has got n vertices, and it has got e edges. So instead of saying that it has got e edges, let me make it a function of the number of vertices and stick on to the value called n minus 1. So I want a graph G which is connected with n vertices and n minus 1 edges, and if you see that, then the graph by default becomes right. Other way around, I am just looking at three properties. One is connectedness, the other one is no circuit, the another is n vertices and n minus 1 edges. Look at these three properties. One is connectedness, the other one is no circuit, graph does not have circuit. The another is the graph with n vertices and n minus 1. Suppose if I insist upon these two, I want a connected graph without a circuit, I want a connected graph without a circuit, then it's guaranteed that if there are n vertices, there must be n minus 1. The implication of these two, the enforcement of these two would imply the third one on the other, right? I don't look at the connectedness, I don't want whether it is, it is immutable for me whether it is connected or disconnected, but my interest would go towards n number of vertices and n minus 1 number of edges, but I want to draw a graph of n vertices and n minus 1 edges without creating any circuit in it. Then it has to be a connected graph.
If you try to enforce these two conditions, if you try to enforce these two properties, then obviously the first property gets enforced. Okay? Now let's try to enforce these two. I want to draw a connected graph. I don't want the graph to be disconnected, but I am supposed to draw how many edges? Only n minus 1 edges. Then you turn up with a graph with no circuit. Look at, basically I am talking about number 1, number 2 put together, number 3, 1 and 2 implies 3, or 1 and 3 implies 2, 2 and 3 implies 1. And whatever the graph is satisfies any of these, any two of these three is a tree graph. Okay? So look, it's a connected graph with no circuit. First two property. It is a cyclic graph, no circuit with n vertices and n minus 1. The last two property. Obviously the first property is cut off. And then it is a connected graph with the first and the last. The second one is indirectly met out. So based on this, on the other end, in the background of this, I can say a graph in which you take any two vertices on the graph, which is a tree, and if you want to travel, if you want to make a journey all along in any way from this source to a destination, then you can walk in only one path, right? And such a graph is what is called a tree graph on the other hand, right? So when you say it is acyclic, when you say it is with no circuit, take up the source, take up the destination, and because of no cycle, you can walk from here to there in only one way. A graph in which there is only one, right? One and only one path between every pair of vertices is what is called a tree graph, right? So on the other road, you can also look at a tree is minimally connected. What do you mean by minimally connected? I want you to draw or to make use of as minimum as possible the number of edges to see that the graph of n vertex is connected. If you include extra edge, then it loses its tree property because cycle gets introduced. And in case if you eliminate an edge from the tree, then the graph gets disconnected, right? You just think of a tree outside. I don't think any two branches will meet again. Or if you just ask about first standard kid to draw a tree on the page, the kid so nicely draws it in such a way that no two lines meet again, right? Look at, we are here to learn about trees. Already the kids have been practicing, more about how to draw. And the other by nature itself, if you cut a branch at any point, then you have two disconnected parts of the tree. You just imagine a natural tree, right? You just climb up, cut a tree in any position, in any branch, then obviously the moment it is cut off, you will have how many components? Two components. Suddenly it gets disconnected. So removal of any edge from the tree causes the graph to be disconnected. Okay, addition of extra edge into that existing tree introduces a circuit in the graph. That's why we call it as minimally connected. So now let's define with respect to a graph G. I have a graph G. Imagine there are number of vertices, n number of vertices with e number of edges. That's what the graph G. I am now thinking of exploring all possible subgraphs of the G which are trees. You take one vertex, take another vertex, and if there is an edge, extract that edge, and then you think of two vertices graph with an edge. It is a subgraph. Is it a tree or not? Yes, it is a tree. You think of three vertices where this is connected to this and this is connected to this. In case if this is connected to this, don't consider this cycle. Take only these two edges and these three vertices, put them aside, then that turns out to be a tree subgraph of the graph G. Now I want you to explore and extract all possible such tree subgraphs. Then when the maximum? One vertex, two vertices, three vertices, four vertices, five vertices, etc. Then you can end up in how many maximum? N number of vertices, then n minus 1 number of edges, and such a tree, subgraph of the graph G is what is called as spanning tree. I mean, the concept of spanning tree is defined only with respect to a connected graph. Without having in mind the concept of a connected graph, we should never think of defining the spanning tree. I mean, the concept of spanning tree arises only when you have a graph G first. A graph G first, right? You think of any general graph, a graph of n vertices and e number of edges. Then my question is to extract only those subgraphs which are trace of this G. What is the maximum a subgraph which is a tree? And such a maximal subgraph which is a tree is called a spanning tree. A tree subgraph of G containing all vertices of G. I want all n vertices to be considered, but still I want to extract only those edges present in the graph G, such that those selected edges will make a tree, and that's what the maximal subgraph of the graph G. And such a maximal tree subgraph of G is what is called a spanning tree. How many such maximal subgraphs are possible? How many such maximal subgraphs are possible? Look at here is an example for you. So we have about a graph with 7 vertices. A graph with 7 vertices. Okay, there are some edges which are in bold, right? We just look at only that subgraph. Look at only that subgraph made up of those bold edges. Do you think that those bold edges connect all vertices? Yes or no? Okay, do you think that that bold edges connect all vertices? Yes, this here is connects, and so on. You concentrate only on these edges and 7 vertices, and that becomes a subgraph of the entire graph G. And such a maximal tree subgraph is what is called a spanning tree. And that spanning tree sometimes, more often, in the other way around, is called the skeleton of G. Is called a skeleton of G. I just want you to write on the skeleton of a human being. How do you write? You put a dot at the top, and then an edge coming down. There is another vertex with a degree 1, 2, 3, 4 above, right? That represents neck. And then you draw a vertical line, and then you draw 2 more lines representing legs, and that's what is called a tree representation of the body of a human being, right? That is what is called a spanning tree of a human being, a skeleton of a human being. So most often, that spanning tree is called a skeleton of G. How many such skeletons are possible for a graph G? Is my question. Right? But I am not interested in all possible such skeletons, but I am interested in only a particular skeleton of a graph G. How do I define the particularity of it? How do I express the property of the skeleton of my interest? Then we go for associating weights with the edges, and based on the weights with the edges, I can define this is what the spanning tree of my interest, this is what the skeleton of my interest. A skeleton of my interest is expected to satisfy these properties. I express the property, and then I go in search of the skeleton which satisfies the required properties, right? I will come to that later. Anyway, look at here is a graph, and when we speak about a spanning tree, we have to first pursue what is really a graph G of my interest, and then what are the possible spanning trees. So spanning tree in general is nothing but maximal tree subgraph of it. Look at this graph now. And consider that spanning tree D. Look at the graph G only. Now look at only the tree which is marked well. Can you observe? Can you observe the spanning tree clearly? Okay? So with respect to the spanning tree, the edge set can be partitioned into 2 disjoint subsets. Do you agree? Okay, what are those 2 disjoint subsets? the tree, and the other subset consisting the edges which do not participate in the spanning tree, right? There are some e number of edges. Out of e number of edges, only n minus 1 number of edges are included in the spanning tree, and rest of e minus n minus 1, I mean e minus n plus 1 number of edges are not considered under the spanning tree. I mean the edge set E can be partitioned into two disjoint subsets such that the one consists all those which are participated in the spanning tree, which we generally call a branch set. The edges which are considered as edges in the spanning tree are called branches of the tree, and such a set, a subset of edges, is called a branch set. The other one is what is called a bar set. Take it in. Okay, quickly we have about 13 edges in the graph and 7 vertices. Because the number of vertices is 7, obviously the number of branches is 7 minus 1, 6. So there are 6 branches, and out of 13 edges, 6 have been taken off as branches, then the remaining would go towards the chord set. Then the chord set has got how many? 7. Look at the number of branches included in the spanning tree is what is called the rank of the graph. Okay? The identity parameter I said here, this indicates the number of components, this indicates the number of vertices, this indicates the number of edges, this indicates number of components. In case of a connected graph, the K is, in case of a connected graph, K is 1, then rank is nothing but always n minus 1, because the number of branches in a tree of n vertices is n minus 1. Okay? And here, in case of a disconnected graph, okay? In case of a disconnected graph of K number of components, then you apply the same theory, I want a spanning tree for this disconnected component, I want another spanning tree for this second component, for third component, and so on. And if you, then instead of having one tree, you will be with a collection of trees, I mean a forest of K trees. And if you want all K trees to be merged together, then you have to draw how many extra edges? K minus 1 edges. Then totally out of n number of vertices, you have n minus k number of branches in the forest of trees, right? So in case of a single connected k equals 1, we call it as a spanning tree. In case of k more than 1, in case of a graph with k more than 1, I mean disconnected, then we call it as a spanning forest. I mean if there are 3 components, this side one, the middle one, and the third one. I think of one spanning tree here, the other spanning tree here, and another spanning tree. Totally, when I count the number of vertices in this classroom, then I say there are n in number. If I think of one spanning tree covering all, then there must be n minus 1 edges, and here is one edge is missing because it is a disconnected component now. So then it is n minus 2. Here is another edge is missing because it is again a disconnected component. Then it becomes n minus 3. That 3 is nothing other than number of disconnected components. So let me put it in general as k. Then in general, the rank of a graph G, whether it is connected or disconnected, is n minus k. Look, sometimes the graph gets characterized by the rank n minus k. Could I get it? And number of edges which do not participate in the spanning tree is what is called the cardinality of the chord set. The cardinality of the chord set is called mu, the nullity. Then this finds an interesting application, particularly in software development. This most often is called cyclomatic complexity of the graph. More the number of chords that you have in your graph, the complex would be the degree of complexity of the graph is so high. In case if you map your program into a graph, every program can be approximated by a graph structure because the flow of control represents the direction of the edge. So every program can be represented as a diagram, right? The moment you represent it as a diagram, then you think of a spanning tree. Then the number of edges participate in the spanning tree is the rank of your program, and number of edges which do not participate in the spanning tree is called the cardinality of the chord set. That's what is called nullity. If the more the number of edges which do not participate in the spanning tree, more effort that you have to put in for debugging the software. the more is the effort required to put in by a programmer to test the software fully. I mean, as nullity increases, the effort to be put in by the programmers to test the software exhaustively increases. Look at, that's what is called cyclomatic complexity. Ultimate job is to see that your program will be with less cyclomatic complexity. But anyway, let me not go into the application of this, but with respect to this spanning tree, given a graph G and a spanning tree T, with respect to the T, the head set can be partitioned into two disjoint subsets. One is called a branch set, the other one is called the chord set. The size of the chord set, I mean the cardinality of the branch set is called the rank of the graph, and cardinality of the chord set is called nullity of the graph. Did you get it? Pardon? With respect to spanning tree, I will partition. I cannot partition the vertices because all vertices are supposed to be partitioned by each other, right? Right. No, you are supposed to mention all vertices. Vertex set doesn't get partitioned because all vertices are included in the spanning. Right? I am looking at a tree containing all vertices. Then if there are any vertices, your tree is supposed to have all vertices. Then definitely that the set V doesn't get partitioned. But on the other hand, the head set get automatically partitioned. Okay, little later I speak about partitioning of vertices also. Okay. When I speak about actual algorithm for generating the minimum spanning, right? Is this concept very clear? Okay, this is very much required for me to continue and to discuss about the philosophy of algorithms to find minimum spanning. Suppose I take one chord. You choose any chord of your interest. Add back to the span. Add back to the graph, right? I mean, currently you are only spanning tree T, only those branches. Now take a chord, put back into the graph. What happens? Cycle gets created. Such a cycle created because of insertion of a chord is called fundamental cycle, fundamental circuit. I mean, every chord is with its own fundamental circuit. But again, we just take up the chord even. We just take up the chord even, add there. The moment you add the chord even, then even B4 and B3 becomes a circuit. And such a circuit is what is called. Such a circuit is what is called a fundamental circuit defined by chord even. Similarly, we define a fundamental circuit with respect to chord E2, with respect to chord E3, and so on. If there are mu number of chords, then your graph has got how many fundamental circuits? Mu number of fundamental circuits. That doesn't mean that mu is the number of circuits present in the graph. Mu is the number of fundamental circuits. The number of circuits in the graph is more than the mu. But I am not concentrating on all such circuits present in the graph, but my interest will go towards only those which are called fundamental, because the other circuits can be obtained by these fundamental circuits in a linear combination. Did I get it? So, by the use of linear transformations of these fundamental circuits, and if you operate these, particularly the exclusive operations on these fundamental circuits, you can get other circuits generated in the graph. If your graph has got some p number of circuits, you need not have to generate all p circuits and store in the memory. You are going to generate only how many? Mu number of fundamental circuits, store in the computer in the form of a circuit matrix, and as and when you want other circuit, you can get it generated just by performing exclusive OR operations on these fundamental circuits.
So we add only one edge at a time.
You have to add only one chord at a time. Which edge you are supposed to add? The chord, the one which doesn't participate in the spanning.
So we will remove that one, again we will add.
No, that will come to the detail later. My interest is
if you add two chords at a time, then we have
no. If you add two chords at a time, each individual chord generates its own fundamental, and another edge generates another fundamental. But addition of two need not result in two fundamental circuits. It may introduce extra circuits also. But the extra circuits are not fundamental. That's what I am telling you now. You can use two or more fundamental circuits, operate on them, especially in the exclusive or function, to generate some more. Okay, you got it? Okay. So, but they are not fundamental. They can be expressed in the form of these fundamentals. With a linear combination of these fundamental circuits, I can generate some more circuits. And one thing, look at the chord set and branch set are not fixed up for a graph G. The chord set and branch set varies from spanning tree to a spanning tree. Instead of considering the spanning tree, you may consider a different spanning tree. When you consider a different spanning tree, obviously you will have a different set of branches and a different set of chords. But one thing is certain, when there is a spanning tree, we can partition the head set into two, a branch set and a chord set, and if you add a chord back to this spanning tree, it creates one circuit, and such a circuit is what is called a fundamental circuit. If there are mu number of chords, there are mu number of fundamental circuits. Could you get it? And the one which is fundamental with respect to spanning tree, one need not be a fundamental with respect to a spanning tree. Two, I mean the fundamental property of any circuit is defined only with respect to a particular spanning tree T. Okay? So I am always speaking with respect to a particular spanning tree. So with respect to this spanning tree, you need to accept E7 of the chords. Add back those one by one, addition of them generates the respective fundamental circuits. So totally this graph has got how many fundamental circuits? 7 fundamental circuits. You may have more than 7 circuits in the graph. Did I get it? You may have more than 7 circuits in the graph. So this is what all about addition of a chord results with a circuit. This is understood? Addition of a chord results with a circuit. And let us now, instead of thinking of a addition of a chord, what I now think of deletion of a branch. Hope you are following it. I have a spanning tree. I thought of adding a chord. When I have added up a chord, it creates a circuit. That's what I said, a fundamental. Now, think of a spanning tree. Don't add anything from the chord set. Instead, think of deleting a branch from the spanning tree. What happens to the spanning tree? I mean, automatically the vertex gets partitioned into two. The moment it is disconnected, the set V is partitioned into V1 and V2. Could I get it? And this is one disconnected sub-spanning tree, and this is another disconnected sub-spanning tree. Could I get it? So, look at here is a branch. And think of choosing only those chords from the chord set which connect one vertex in this group, another vertex from this group. Hope you are following it up. Or should I draw the graph on the board? Not necessary, no? On the other hand, let me assume that you are all individually vertices. Every one of you is a vertex for me. Your friendship is the adjacencies. Then what I do? I cut off all friendship between this group of people and this group of people. Could I get it? I cut off all friendship existing between this group of people and this group of people. Now I got two disconnected. So assume that here is a spanning tree. I worked out a spanning tree across. I worked out one spanning tree here. Then I established the edge between these two. Then this is a complete spanning tree covering both. Is it a branch or not? Yes or no? This is a branch. And all other friendship between any one of you this side and any one of you this side, they are considered to be a branch or chords? Chords, right? If that guy has got a friendship with her, then that is got a chord with respect to this spanning tree, right? Yes or no? So this is the only branch present. Then if I cut off this branch, then the spanning tree gets disconnected into two, and rest of the links between this chord and this chord are called chords. Look at the family of dead chords and this branch put together is what is called a cut set. Right? So what do you mean by cut set? Cut set is set of those edges along with this branch, which makes removal of them, makes the graph disconnected. The vertex set B is decomposed into two disjoint subsets V1 and V2. The edges, the minimal number of edges to be removed to split the graph G into G1 and G2 disconnected is what is called a cut set. Okay? So when we speak about cut set, source destination cut we speak about. What do you mean by source destination cut? Suppose Pakistan wants to disconnect the communication exists in between the famous capital in India called Bangalore, right, and Delhi presently. The Pakistan wants to go more some of the places so that there should not be a communication between Bangalore and Delhi. Does Pakistan go for minimizing the effort or maximizing the effort required? Minimizing. Then it looks for only cuts. The minimal number of edges will be removed so that the communication can completely be destroyed. Okay? So I think somebody might have spoken about a source destination pair, right? The source destination pair is just a question of what? Identifying a branch and associated plots so that the number of plots in the branch will be minimum so that I can establish the graph. I can see that the graph is disconnected. Okay? On the other hand, because of earthquake, Japan now is in a serious situation. So later, after 1 or 2 years, Japan wants to get established. Then it wants that Japan wants to see that there will be connectivity across all cities in Japan later. But initially, it will not go for maximum number of communication. But initially, it seeks to have minimum as possible, but still establishing connectivity across all cities. I want all cities to be connected, but the connectivity establishment should be done with minimum number of effort, right? With less effort, then it looks for a spanning tree. I want minimally connected. Effort should be minimum, but still I want all cities to be connected. Spoiling is a question of cut set. Establishment is a question of what? Okay, anyway, so with respect to spanning tree, generally the X set is partition, one is called a branch, the other one is a part set. Addition of a chord introduces a circuit called a fundamental circuit. Deletion of a branch makes the graph disconnected, and the branch and other parts to be removed, is what is called a cut set of the graph. Look at here. Suppose I have this, a simple graph. I have this simple graph. So if this is a spanning tree. Right? This is spanning. Okay, if I just cut the graph like this, how many branches are included? How many branches? How many edges participating here? 1, 2, 3. Out of these 3, how many branches are there? 1 branch, right? These are the branches. 1, 2, 3, 4. The edges participating in the spanning tree are called branches, and these are chords. So look at. The set of edges to be removed to disconnect or to make the graph disconnected along with the branch is what is called a cut set. These two are the chords, and this is the only one which is called a branch. Is it a cut set? Yes, because this gets isolated, right? Is it a cut set? Yes, because this gets isolated. Now notice the difference between this cut set and this cut set. What is the interesting property of this cut set? The interesting property of this cut set is that there is only one branch, but rest of them are all chords. Whereas here there are 2 branches. A cut set consisting of single branch is called a fundamental cut set, and rest of the cut sets are all non-fundamental. The way in which we define a fundamental circuit, which consists what? One chord and the remaining are all branches. One chord and remaining are all branches. Look at this. If I add a chord, it becomes a circuit. Here there are many branches but single chord, right? A single chord, many branches is one family called a fundamental circuit. A single branch and many chords is what is called a fundamental cut set. Hope you understand now. Okay? So these are the very important things that you have to remember till I speak about the algorithms for minimal spanning trees. In fact, the philosophy of finding out minimal spanning tree lies only in this, a fundamental circuit and a fundamental cut set. Okay? How do I find a spanning tree? Is my question. Any simple way of finding out a You are removing what it is? Which it is? Pardon? Which are parts of the cycle? I mean, your job is to find a cycle. What's your job? Finding a circuit. If a graph G has got a circuit, delete one edge from the circuit. The moment an edge is deleted from the circuit gets opened. I mean, as long as you find a circuit in the graph G, your job is to remove. I mean, when G has a circuit, remove, delete an edge from the circuit, right? When G has a circuit, delete an edge from the circuit. That's the end of the algorithm. The moment you feel that G has no circuit, stop doing it. Then you end up in scanning. The sequence with which you delete edges, that makes the difference. 1, 2, 3 are the edges to be deleted. I go in the sequence 1, 2, 3. Somebody may go in the sequence 2, 3, 1. Somebody may go in the sequence 3, 3, 4. Somebody may go in the sequence 5, 6, 7. Right? What are those edges you select from a circuit? There is a circuit ABC. You may think of deleting A. I may think of deleting B. Somebody may think of deleting C. What edges you select, that matters to come out with a particular spanning. Anyway, if there is a circuit, the job is to see that the circuit is opened by deleting an edge. You do this how many times? I do it. And the other one, my question is the following: how many times this while loop runs? Come on. As many circuits. Suppose there are p number of circuits. How many times this while loop runs? Now think and answer, please. Come on. Come on. Read louder, please. Nullity. You need not go for as many circuits as they are. It is quite enough to spoil only fundamental circuits, because the rest of the circuits can be expressed in a linear combination of these fundamental circuits, right? If you spoil these fundamental circuits, then all circuits are indirectly spoiled, right? Yes or no? Following it up or not? You need not go for, right? It is good enough to spoil only those which are called fundamental. How many fundamental circuits this graph has? As many chords as there are, right? Yes or no? That's nothing but the psychological number. That's nothing but the nullity. I mean, this algorithm has got the complexity. Oh, we had a first lecture on complexity theory, right? Yes or no? Well, if not, let me just take up this. This is a branch. 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 1, 2, 3, 4, 5, 6, 7. There are 8 vertices. Yes? 1, 2, 3, 4, 5, 6, 8 vertices. Right? How many branches we have? 7. How many branches which are not included in this? 1, 2, 3, 4, 5. Get it? So how many circuits does this contain, this subgraph contain? One is this triangle, the other one is this triangle, one is this rhombus, right? Is the rhombus a circuit or not? Circuit. This triangle is a circuit. This triangle is a circuit. If you look at only this part of the graph, there are how many circuits? There are how many circuits? 3 circuits. But out these two are called fundamental, and because of these two fundamental, I can get this numbers generated just by doing exclusive OR operations on them, right? Did I get it? I mean, if I want to spoil this, how many edges I have to take away? 2 edges, but not 3. Right? Then this while loop runs how many times? This while loop runs how many times? Number of parts. I mean the null graph. Then is there any chance that it runs less than the null? Yes or no? Is there any chance that this produces a spanning tree? Right? With less number of runs than the nullity? No. Is there any chance that this while loop runs more than the nullity? No. Then this while loop runs exactly equal number of times. When you say that this loop or this algorithm runs exactly so many times, then we denote it by theta. Understand? On the other hand, if you have the tendency or if the algorithm has got the behavior in such a way that sometimes it runs more number of times, sometimes it runs less number of times, right? If it is so fortunate that it runs with less number of iterations and gives the result, if it is so unfortunate then the algorithm will run more number of times, then it takes a longer time, then you have a notations called the best notation and the worst notation. Best notation is generally denoted by omega and the worst notation is generally denoted by a big O. Do you get it? Okay, let me use omega for best case and then worst big O, and neither best nor worst, always same behavior, then I denote it by theta. You will not see a significant difference between the best case and the worst scenario. Whenever there is no such significant difference between the best situation and the worst situation, then the notation is strict. So, does this have a theta complexity or a big O complexity? This has got a theta complexity. So, my problem is now to generate all spanning trees, not one spanning tree. How do I do it? To start with any spanning graph, you are interested. How do you come out with the spanning graph? Find a circuit, remove one edge element, find a circuit, do it mu number of times. Do it mu number of times. Then you are with one spanning tree. When you are with one spanning tree, add a card back, add this back. What does it create? What does it create? Which circuit?